Bon dia a tothom. Dear colleagues, good morning and welcome everyone to Barcelona and to today's workshop. I'm Miriam Moiset, the ICGC General Manager, and I have to say that we are really happy that all of you are attending this workshop and demonstration here in person at the ICGC or in the live streaming that we are performing. So thank you for coming and joining us. Today, the consortium formed by Rokubun and the ICGC is going to present the Union project. The technology developed and the results obtained after 2 years, now that the project is reaching its end. We would like to thank the EUSPA, the EU Agency for the Space Program, as this is research and development, a European project funded by the agency. Union, as the acronym of Undifferenced and UNcombIned Positioning Engine, is a new satellite positioning technology with the goal to provide accurate navigation for mass market devices. But without forgetting about the current user of positioning services as the ones who trust on the Catalan Integrated Geodetic Positioning Service provided by the ICGC. Just to give all of you a brief idea on the technology, let me say that Union is based on leveraging the strength of RTK and PPP techniques, plus the Galileo high accuracy service, palliating some of the main limitations of those techniques when used separately, such as the poor scalability of RTK and the slow convergence time of PPP. All this will be shown and explained in more detail in the following presentation. This project has been very important for the ICGC, who is currently operating the Catalan Integrated Geodetic Positioning Service and the active GNSS CatNet network with all its services. In this regard, it is necessary to say that the CatNet network is one of the 3 pillars of the Union project, and in the opposite direction, the UNIT project is one findable way to expand the CatNet positioning services into this mass market world. Last but not least, the Union project is completely in line with the positioning services currently provided by the ICGC, coherent with their accuracies and consistent with the official ETRS 89 reference frame published and maintained by the ICGC. I want to say thank you to Joel and Jordi Sánchez, David Gómez, la Laura Serra y la Agnès Lladós to organize this commit. Thank you.
Thank you, everybody, for joining today's Union workshop and demonstration. I will just thank also Miriam Moiset for this nice introduction of the project. And right now, I will just move to the first presentation. But before this, I would like to introduce our first speaker, who is Miquel García Fernández. Just to give a brief introduction of him, just to say that he's the co-founder and CTO of Rokubun. He's a GNSS research engineer with more than 15 years of experience. He received his Bachelor of Science in Telecommunication Engineering in 1999 and his PhD in 2004. Related to GNSS data processing, both issued by the Polytechnic University of Catalonia. His most recent experience before co-founding Rokubun includes a position at JPL in the NASA, a postdoctoral position in Research Center for Sustainable Humanosphere in the University of Kyoto, a contract as scientist in the GNSS Technology and Navigation Group of the German Aerospace Center, and the position as a project and program manager in Starlab Barcelona. He's also an associate editor of the GPS Solutions Journal. And without any further delay, I would like to introduce the first presentation, which is the Union New Strategies in GNSS Technology for Accurate and Scalable Applications. Mikel, the floor is yours.
Okay, Houston, you hear me? Yes, vale. All right, so thanks, Joel, for this nice introduction. So I'll be talking around 15 to 20 minutes, hopefully less, just to give you some insights of what is Union, right? So what we have been doing in these last 2 years with ICGC, what are the objectives of the project, what have we achieved, so that you have a brief idea of the framework of this project, right? So let's start with definitions, right? So what is a union? So Miriam before mentioned the acronym, but if we have to summarize it in one sentence, long sentence, maybe we can use that one. So Union is a satellite positioning engine for accurate and real-time navigation for mass market devices, such as smartphones and vehicles. For those of you who are already curious about that, just feel free to browse to this webpage. So there are actually 2 keywords in this sentence that I'd like to highlight. One is accurate and real-time, and mass market. These are the 3 keywords that we want to stress in this presentation. All right, so I mentioned a sentence, but what does it mean in practice, right? So what are the objectives that we wanted to achieve, and what we have achieved at the end, right? So basically we wanted to fulfill these 3 objectives. So we wanted to develop a positioning engine that it's flexible, that it can cope with the new signals that are out there in GNSS. We want to achieve decimetric accuracy. When we say accurate navigation, what do we mean, right? In practice, we mean decimetric accuracy in mass market devices. As you will see, decimetric depends on the environment, obviously. It's not the same an automotive receiver than a mass market receiver such as a smartphone. So decimetric accuracy works for premium mass market devices such as u-blox chipsets and low-end GNSS receiver, but being more realistic for devices such as smartphones or wearables, decimetric accuracy is really a challenge. So we are targeting more on the meter level accuracy. And finally, one of the issues that was briefly mentioned before in Miriam's presentation was to overcome the scalability of current position technologies, such as RTK. We'll talk a bit more about that later, and I think Joel will also make a presentation about that. So in terms of metrics, right, what are those? How do we translate those objectives into metrics? So basically in 3 of them, right? So we want to ensure continuity so that we have a consistent, accurate positioning during long ranges. We are talking hundreds of kilometers in RTK networks where you have handovers between stations. This accuracy can be impacted, so we want to at least ensure that we have a continuous flow of accurate navigation over long distances. We want also accuracy. That's kind of the de facto metric for all positioning engines, right? We want decimetric accuracy for automotive and metric level accuracy for lower grade receivers, such as the ones we can find in smartphones. And finally, tied to continuity, we want also availability. So we want to maximize as much as possible the availability, so the points at which we have positions and we don't have parts of the territory with a lower degree of accuracy. All right, so it's just to give some figures about the project itself, right? So as Miriam mentioned before, this project is a two-partner consortium. It was ICGC on the one hand, and Rokubun, who was leading on the other side. So Rokubun put the idea on the table, put some development as well, while ICGC was basically providing the infrastructure of the base stations, as well as the infrastructure to generate the virtual reference stations, which we will give more details later on. So this is a combined effort between these two institutions. So it's a private-public effort, as you can see. The project lasted 2 years, or is going to last 2 years. It's not yet finished. It will finish soon, but not yet. So it started on March the 2021, and it will end by the end of February this year. So total of 2 years, and a total budget of less than $500,000 split between the two partners. It has, I would say, a rather classic approach in terms of work packages. We have a definition stage where we define the network that we want to implement. We define the algorithm we want to implement. Then it was followed by the detailed design, right? So we would put the specific details on what we wanted to implement. Obviously, it has a development stage where all the effort basically was concentrated. And obviously, after the development, you have to test the outcome. So there is a test and validation phase for that. Obviously, being public grants, it has to have a dissemination stage where we publish our results, disseminate our results into conferences, and finally, so there is an important work package, which is the commercialization. So we don't want this project to be left in a drawer somewhere. We want to have some market viability out of it. So part of the project also was obviously to try to find a business model behind the exploitation of the results of this project. So basically, just to get into more like technical details, so we mentioned there are two things here, accuracy and scalability. So there are two concepts in the project. There is one part which is a positioning algorithm, and there is another part which is scalability of the service. Regarding the algorithm, we call it Undifferenced and UNcombIned processing engine. Assuming that you are here and you're familiar with the GNSS technology, you already know that there are kind of the state of the art in terms of algorithms is that you have precise point positioning, which typically uses the ionospheric combination to get rid of the ionospheric delay, and so on and so forth. So it combines the measurement of the GNSS receiver. And then you have the other alternative, which is the real-time kinematic, which, as you may know, it uses data from a reference station, and it makes differences between the base station and the rover. So you can see two words here, combined and difference. Which word rate? Well, the GNSS world was simple. So you had GPS, 2 frequencies only. So things were rather simple in the past, but they are not simple anymore. You have GPS, you have Galileo, Beidou, you have many more constellations, you have many more signals, you have many more frequencies. So now the question is, what should I combine, right? I have to take one reference code, right? Or what should I difference? I have to take which satellite, right? So the bookkeeping, it comes very cumbersome, more complicated. So now there is this trend of, instead of combining and differencing data, just process the data as is, right? It makes a little bit more complex, the processing, because when you combine or when you difference data, you remove things that you are not interested, right? But you don't have it anymore when you process the measurements as is. So you have the troposphere, you have the ionosphere, you have some biases. So what do you do with those, right? So what you have to do is estimate them. So you don't remove it, but they are still there. You have to estimate it. But you can do that, right? You have more signals, you have additional data, so you can do that. This approach is not invented by Rokubun, so it has been in literature for some years already, but at an academic level. What we have done in Union is bring those knowledge and implement it so that it can be a commercial and viable technology. Okay, so I've talked about the algorithm. Now, just some few words on the service. And I won't mention too much because then I don't want to step over Joel's presentation. Just to let you know that what we have implemented in Union is what we call permanent virtual reference station concept. So as you know, in RTK, this is a bidirectional system, right? So you have a rover receiver you want to position, and then you have a set of base stations and the service that provides corrections for that rover. The rover needs to send an approximate position to the service, and the service will compute a kind of stream of data that is suitable for that receiver. This works fine when the number of users is relatively moderate, but as you can imagine, for mass market applications where you have millions of devices, maybe not millions, but hundreds of thousands of users in a very small area, this can become a problem, right? So you have to try to be like as much broadcast as possible without interacting too much with the users. So that's where the permanent VRS comes into play. Instead of making the user send the position and then replying with a stream, we set a predefined set of stations, right? It's the map that you see here. So we configure the network, ensuring that the baseline is 20 kilometers, and then we provide these virtual stations to the users. The user simply has to connect to the 2 or 3 stations that are closest to him. Right? This is scalable because there is no bidirectional nature here. It's just one way, right? So it's from network to the user. Right? So how does it translate in practice, right? So what we have basically done is create a caster, right, with all the base stations, virtual base stations that are provided by the service. So we will see here in the caster the stations from ICGC, right? And from then on, you'll see all the virtual base stations. So the user would basically pick the ones that are closer to him or her. So another part of the project that has been done is working with a Galileo high accuracy service. As you know, a HAS is a concept that it's already broadcast by Galileo. It's a signal, it's a series of data that is broadcast in the E6 frequency of Galileo. And these are basically corrections on the broadcast orbits, clocks, and DCB biases. Right? So USPA is validating it. Actually, it finishes the validation and it's already broadcasting the data as we speak. And in the context of Union, Galileo has been implemented the processing of the Galileo HAS into our filter, and we just participated in the validation campaign that has been done during the execution of Union. All right, so here you have an example of processing some data for a professional receiver. This is a septentrial aesthetics. This is basically horizontal error, the cumulative density function, if you use HAS or if you don't use it. So as you can see, basically by applying these extra corrections coming from the Galileo HAS, you can really remove the error quite substantially. Right? So one of the activities that were done in Union, besides validating that, is making these corrections available to non-E6 users, right? So smartphones can track L1. If it's one of the flagship receivers, maybe you can track L1 and E5 if you're lucky, right? Other receivers like U-Blocks, they can track L1 or E1 and E5B, but E6 is usually limited to geodetic receivers, so really expensive receivers. So low-cost, medium-cost receivers won't typically have access to E6 frequency. So what about them? they cannot access to E6. So one of the things that actually USPA is also trying to do it is recast or rebroadcasting this information through internet. So we actually did that as well in the Union project. So basically what we did is we have a septentrion receiver in our premises. We just take this E6 data, or the HAS within the E6 data. We convert it to standard RTCM3 format, and then we rebroadcast it through the Union caster. That's what actually you see here in this line, right? So there is an extra line in the caster that is an SSR stream, right? So a receiver could basically connect to that mount point and would obtain RTCM3 messages with the HAS corrections. This is already implemented and it's publicly available. So now this means that a smartphone that it's only L1, as long as it has internet connection, can connect to that and have access to the SSR corrections provided by Galileo. So another thing that has been done, especially because we had to develop the algorithm and test it, right? So we basically implemented that as low level as we could. So basically all the algorithms are implemented in C, which maximizes our possibilities to cross-compile it in different platforms. We can try it on laptops, we can try it on desktops, but actually we wanted to embed that into our receiver, which is an ARM-based receiver, and also to Android smartphones. Implementing the whole thing in C allows us to make this cross-compilation much easier. This allowed us to make extensive test and validation campaign. So we tried multiple scenarios: bicycle, pedestrian, with a smartphone, and with Medea we used automotive campaigns that lasted like 100 kilometers or more. So this had been actually done for the project as well. As I mentioned before, there is a part of dissemination in this project. So we presented this concept in conferences, published some papers in UNcombIned, had some press releases as well in order to let the concept be known. We also performed several infographies trying to explain the concept behind Union on a more commercial level. And finally, commercialization. This is a key point of the project. So that's the whole point, especially for Rokubun, right? At the end of the day, we have to somehow make the concept available to the market. No? So we mentioned, we created the commercial name for the Undifferenced and UNcombIned processing engine. We call it SPEAR. There is also an infographic in our webpage, in Rokubun's webpage, if you are curious. And all the validation testing that we've been performing in Union, it's actually being used to prepare a white paper. A white paper is basically a document that we are using to approach the industry and say, hey, this is the accuracy you can get in this scenario and this other scenario with this platform or this other platform. So we are taking this tool as a means to prove the accuracy and the availability of this algorithm, because there is actually some need of that. So there are chip manufacturers, chip integrators that they implement the hardware, but at the end of the day, they lack the expertise of processing the data itself. So there is actually a need to develop or license some algorithms that can make most of the hardware. That's our market goal in terms of the location stack or the algorithms. So in fact, we just signed a few weeks ago a collaboration agreement that is currently ongoing of an initial integration of this processing algorithm into a navigation onboard unit. So we are step by step coming in here in the commercialization phase. Besides this, we are also working on expanding the permanent virtual reference station to more territories, right? So can we exploit that? Can we make some money out of it? So these are questions that we will try to answer by the end of the project and a little bit with further project as well. So thanks a lot. I hope I didn't, well, I just took 6 minutes from you as well. Sorry about that. In case you have any questions, just feel free to browse the web or just ask me, or I'll be around here. Thank you. Excuse me, thanks.
Thank you, Miguel, for this nice introduction and presentation of the project. I will move to the next presentation. Just before this, I would like to introduce myself for all of you who do not know me. I'm Joan Grau-Bellet. I'm the head of the geodesy unit here at the Cartographic and Geological Institute of Catalonia, with more than 15 years of experience in geodesy and surveying. I received my Master of Science in Geodesy and Cartography in 2005 from the Valencia Polytechnic University, after having obtained my Bachelor of Science in Surveying in 2002 from the Polytechnic University of Catalonia. Just to give a brief example, I have to say that together with my colleagues, I've been in charge of calculating and disseminating the ED50 reference system update to ITRS 89. And I think I have to emphasize one of our most recent achievements, which is the acceptance of ICGC as an EUREF dedicated analysis center. I think that this has been a very important achievement for us, so just to share it with all of you. And without any further delays, I will start with the presentation. Mikael already been talking about the permanent virtual reference station new concept. I would like to go a little bit more in detail. Okay, sorry for the technical issues. Just briefly, because for sure most of you already know CatNet network, but just to give you a brief idea of the current status of the network, just to say that all stations in the CatNet network are already tracking GPS GLONASS, Galileo, and Beidou constellations with the receivers with the full capabilities. Already stations have geodetic and individual calibrated antennas mounted on it, all of them. And just to point that most of them are connected through 4G with ICGC facilities, but in some of them we already have LAN connectivity. And also just to point perhaps the most important services that we already have in CatNet, just to focus on nTrip, which has been very important for this project, and the geophones and the Rinex shop, which are just for post-processing users. In fact, the virtual reference station concept, which is the classical concept that we have been already using for so many years, just to move on, just to say that this service is working on this way. I mean, servers at ICGC are creating virtual reference stations for each user in its coordinates. So the user just needs to send the approximate coordinates. And the servers here at ICGC just create the virtual stations and start sending data to the users. The problem, as Mikael said before here, could be the scalability of the solution. With the users that we have right now, this is not a big deal, but what if we are facing the mass market approximation? I will talk more in depth about this on my next presentation, which is the current status of the real-time service at ICGC and the scalability for the future. But here we are for just letting you know about the new concept that the union proposes, which is the permanent virtual reference station concept, which is meant to have no scalability limitations in the main sense of the concept, which should allow also the interterritorial navigation when joined together with PPP, and as perfectly explained, Mikel, also including Galileo HAS, just to make these observations available to all the receivers that are not capable of doing it by its own means. This is just to give you the concept of the idea, behind the idea. The permanent virtual reference station concept consists in the creation of a regular grid of virtual reference stations, just understanding the concept as the classical one. We have designed the solution just to have a grid spacing of 20 by 20 kilometers, which we understand and should be enough to fulfill the BRS-like accuracy. And these are the stations which are called the permanent virtual reference stations. These are published in the UNCaster, as you have probably seen on the presentation before. So any user will have at least 3 stations closer than 20 kilometers. This, we understand, it's enough just to provide a time to first fix similar to the one that we are obtaining with the BRS classical concept. Users can, or in fact have to choose and connect to the closest available stations, and here is where the positioning engine that's going to be described after this is going to enter in play. There is no need to send coordinates, as on the classical concept, as all the permanent virtual reference stations required are already available and accessible to everybody. So the users are capable of choosing the closest station according to its position. There's no need to transfer this need to the server. So the server does not need to create a new virtual station for each user, as all of them are already in place. You have seen this map before. This is just the grid that we have created here, just covering Catalonia. This is the naming that we have thought that could be useful for this. And why this naming? Because this naming allows us to go worldwide. I mean, we are using 4 digits, which is the usual way to identify permanent stations. And we are using the station where we are moving each character from A to Z and 1 to 9. And this allows us to move with this spacing all over the world. So we have plenty of stations, a grid of 20 by 20 kilometers, which covers all the world. So in case we need to go to any other place, we just continue using the same naming with the same software, with the same concept. This is the idea. Here, just to show you what I've been saying, the permanent virtual reference stations are created as if they were working in the field. This is the software that we're using to manage the stations and the service. As you can see here, we have the physical networks, J, Abel, Bell, Sona, and Sorg. These are the stations. And this grid are the permanent virtual reference stations. As you can see, all of them are created from a single stations as if they were virtual reference stations. The data that we are getting from these stations is the one that we are broadcasting to the UNCaster. In fact, it's exactly the same as if they were users, so they are already created and they are already available. And this is the way that it performs the Union and Tripcaster when these stations are available. Union and Tripcaster provides access to all these synthetical stations. Nowadays, as I said, the CANDEN network is the one providing the corrections, but the tool works with any other similar network anywhere in the world. We're just using standard formats, so you can spread it all over any other place which is using similar services that we're using. Obviously, physical stations are also used in combination with the permanent ones. You can see here more or less the infographic which is showing the grid of permanent stations, also with the classical stations. This data is all going to the Union and Tripcaster, which is then made available to the user. But there's no need, as you can see here on the comparison, to create a specific user station. Here, the main difference between the approximation that we're using nowadays and the approximation that the Union proposes. The first difference is that the communication between the user and the service is no bidirectional in the Union, so we just need to broadcast the corrections, and the user is the responsible for choosing the appropriate ones. The second difference is on the caster, which is just broadcasting the information coming from stations, but here the caster is also waiting for the approximate coordinates on the user, and the other one is obviously the situation from the user point of view. Here, when the user gets access to the data, the server creates a specific virtual reference station for the user, but here it's not the same. I don't care if the user is here or here or here. It's used on a car, on a tractor, on a drone. They will have all the same stations available for it. The permanent VRS system is based on Python software, where we have developed in the consortium, and this is more or less the working structure that we have designed to be. So all the data that the software developed in the project is accessing is already available on the public services. The first one is the data from the VRS3M service, and the other is the data from the stations. All of them, it's full constellation data. As I said, everything is combined in the UNcombIned in-trip caster, which is based on the BKG solution. This is just to give you an example of what we are having with Union permanent virtual reference stations. You can see here the age of the data. All the data provided to users, it's below 1 second. In fact, it's below half of a second. This is the availability of data. Nearly 99.9% of the data, this is for 1 day, has been available to users. And here you can see the number of satellites that we are providing. I have to say that right now we are providing even more Beidou satellites, which are already available for tracking. Just to give the idea of the server that we are using for the Union, because this will be useful on my next presentation just for comparison purposes. The software is solely based on Python, and it is running on an Ubuntu Linux 64-bit server with just 2 CPUs, 4 GB of memory RAM, and 80 GB of disk. But the point is not here, it's here. We are monitoring the usage of the server, and you can see that the CPU usage is 1%. We are just using 2 GB of the 4, and we are just using 15 GB of the 80. Most of them just for the OS. This will be important for the scalability. Just to give finally a brief idea of the accuracy, obviously we are worried for the accuracy of the service that we are deploying. What we have been doing here is just to install a geodetic receiver in a mast that we have here at the rooftop of ICGC headquarters, and we have done some measurements. First of all, with the service publicly available, the VRS3M, which is a full constellation service, and then we have checked this with the 3 closest permanent virtual reference stations available in the area. The receiver was here, and we were checking against these permanent virtual reference stations. You can check here the differences. We are most of times below 5 centimeters, so the value is not important. The most important here to say is that we are quite coherent with the services that we are providing. So we are capable of providing more or less the same accuracy that we are providing with the services already available. And last but not least, my conclusions, just to say that we understand that mass market is feasible. So from the user point of view, it is essentially the same trusted VRS concept, but on a different caster and using the UP, the software that is embedded on the receiver. It's capable of providing the same accuracy as current services. It allows the combination with PPP positioning whenever required for the UNcombIned and undifferenced approach. And it allows using extra services as HAS, and so could be continuous worldwide. Obviously, the accuracy would not be the same if we have permanent stations there or not, but at least we can use the service so we could have positioning. And from the provider point of view, it allows scalability with the same resources. Yeah, we need one additional server just to be able to run the Python code to generate the virtual reference station permanent. It takes benefit from the wide expected extended entry concept. It allows providing extra services embedded in the same cluster, and it allows covering the wall territory. And what we should understand for wall, it's our responsibility to decide it, as we can combine VRS with PPP or with HAS. And that's all for me for this first presentation. So I give back the word to Mikel.
Long time no see. All right. Before this presentation, I'll talk about the concept of the project, or Union project itself. But there is one important key point, at least for Rokubun as a private company, is what is the strategic interest? Why do we want to do that? Right? So, well, yes, we are private. At the end of the day, we have to pay the payrolls and we have to make at least some money, right? So we at least need to make out of it in terms of commercial exploitation. So I'll give some brief vectors on what Union fits in the market in terms of precise positioning, both on the processing engine side and both on the correction service, or the network, if you will. So basically, the thing is, the number of devices that needs geolocation has been increased, I would say, exponentially. Albeit the GNSS technology has been there for us since the 80s, right, with GPS. But with the appearance of first the smartphones, then the cars, then with IoT, so the number of applications have been grown exponentially, right? So this is the context in which we are placed, right? So geolocation of increasingly humongous number, right, of GPS receivers that need to deliver accurate positioning. So as I just briefly mentioned before, so how does Union try to answer this new context, right? So we are trying to approach this field or this segment by making two proposals. One is the SPEAR. So it's basically the provisional allocation stack. I'll mention what allocation stack is, that can be licensed by chip manufacturers. As I mentioned in my previous presentation, there is several groups of hardware manufacturers that they are aware that, okay, they have a very good hardware, but how do we process this data and make most of it, right? So this is an actual need. So SPEAR tries to address this need. Right? So we have an engine, so let's license it. The other one is the network, the permanent virtual reference service. So we have a network, and this can be considered, as we will mention, then as an added value service. This is important because the market for added value services is increasing like a lot, right? Okay, location stack. What is a location stack? Location stack, basically a software library. A software library that can be embedded in devices, in few words, right? So on the bottom hand, you have, on the bottom side here, you have the GNSS or location value chain. So SPEAR, right, the algorithm that we are trying to develop is basically serving these two components in the value chain. So we have a component manufacturer, right? So chips, right? So U-Blocks makes chips, even though they have their own processing engine, but there are others that make chips, but they don't have processing engine. This is the component manufacturers. There is also receiver manufacturers. You can consider them. So yeah, between these and the system integrators, I have one GNSS chip that gives me the measurement. I have another chip that brings the computational power. What do I put in the application processor just to have a good solution in positioning, right? These are the system integrations. So the SPEAR could actually serve system integrators as well, right? Okay. Correction service. What is a correction service? As I mentioned, this is an added value service. It's not a receiver. It's not a piece of hardware. It's something that assists the hardware to give a better positioning. And better can be in terms of accuracy, in terms of time to first fix, for instance, like assisted GNSS. All of these are added value services. Permanent virtual reference station is also an added value service. And just for you to know, the revenue for added value services, right, is increasing it's going to increase like 72% by 2031. So there is a lot of demand for that. There is a lot of companies that are already there. We are obviously not the only ones. We are just teeny tiny, but there are big monsters there that are already providing added value services for that. So in terms of corrections or added value services that rely on correction services, what do we have, right? So we have like two schools or two means of providing corrections to the services. Each one has its own pros and cons, right? We have OSR, which stands for Observation State Representation, and this, as you may know, is basically RTK, right? So the base receivers deliver directly the pseudo-ranges, the observations, to the rover so that then it can perform RTK. This is OSR. SSR is space state representation. Instead of delivering the observations, the service delivers corrections to parameters of for instance, the orbits of the satellites, the clocks, biases, etc. It doesn't provide the full observation of the receivers, of the base receivers. It's just corrections on the products that are already being used by the rover receivers. Galileo HAS is an example of SSR correction, right? RTCM3 streams with SSR corrections is obviously an SSR service provision as well, right? So as we mentioned, there are pros and cons for each of the approaches. In both cases, we are aiming at centimetric accuracy. The main advantage of OSR is fast convergence. Obviously, it's not instantaneous, but almost, right? Whereas SSR has rather lagging in terms of convergence. Can take a while, right? Especially if the ionosphere doesn't help, so you have to converge the biases and so on and so forth, which translates that you want to get the fast convergences as RTK, for instance, right? Which is a matter of seconds or even, yeah. One of the main disadvantages of RTK, and that's why SSR corrections are considered, is the fact that they are not global, right? RTK are limited to 20 kilometers, 50. It depends on the area, but going beyond 50 can be a challenge to get good accuracy, right? So whenever you talk to service providers or hardware manufacturers and you say, there is this technique that's called RTK where you can get centimetric accuracy, the immediate question that you are made is it global? And then you have to explain, nope, it's like 20 kilometers. So then what's the point? The point is that you have to rely to other techniques such as SSR, right? The corrections are valid worldwide. It has its downsides, but at least you get better accuracies that with standalone positioning. Another problems with OSR, which can be overcome as we have seen, is that it's bidirectional. Not with permanent VRS. This is a slight improvement on the technique, right? But SSR, it's a broadcast system. It's a one-to-many approach. You simply just deliver all the corrections for satellite clock orbits and biases. It's true that, for instance, for ionospheric and tropospheric corrections, it's regional, but in general terms, it broadcasts, and another big advantage is that it has low bandwidth. Since you don't have to deliver measurements every 1 second, for instance, then the amount of information that you have to send over internet or over all your channel is way less than in RTK corrections, right? And principle, the problem is that of SSR is that the hardware, well, maybe not 100% compatible. Why? because the messages that are transferred into the SSR might be proprietary. So there are several companies that develop their own messages, SSR messages, but obviously they won't work with all receivers. So this is something else that you have to bear in mind. Just as an example of what's out in the market, so we have OSR providers. OSR, remember, RTK. We have networks, some of them like on a more crowd sourcing, like Onokoi, which is a recent initiative, which is actually followed by GeoTnet. There are several others. And obviously, we have the regional services like ICGC. No? In the case of ICGC, is in principle, it's public, it's free, but so there are private companies that want to make money out of it. If I'm not wrong, the Swiss network is a premium service, so you have to pay to get access to the corrections. So yeah, you have various business models involved here. Example of SSR, there is actually a lot of money invested now in SSR. We have probably Swift Navigation is one of the most recent actually it's not a startup anymore, but it received a big amount of funding to develop this worldwide SSR correction service. We have uBlocks that acquired Subcorda, for instance, which was kind of a consortium initiative, but then uBlocks took control of it, also an SSR provider. And we have also Trimble and Hexagon. I think we have some colleagues out here from Hexagon that could give us some details. All right, so this as far as the added value is concerned. So what about the positioning engine, right? So as I briefly mentioned, there is actually a need for that as well. So there are companies, and here I just put a couple of examples that you can find easily in the web, right? So for instance, ST Microelectronics that makes chips, measurement engines, so to speak. They deliver a good range measurements in the rubber, but just they made an alliance with Point One Navigation to get a partnership to process these measurements and get a good position. And obviously, everything has to be automotive grade, right? It's not only that we can deliver the position, but we have to deliver it with a certain regulatory standards, right? So the software that you can have or that you have to put in a car is not the same as you have to do it for a research activity, for instance. No? So there are some extra constraints that need to be taken into account. There is this other company, Kectel, as well, that it's a system integrator, is one of these examples of system integrators that have several pieces, measurement engine, application processor, and then they lack the hardware, the software, sorry, to process these measurements. So the industry, the hardware industry, is already looking for solutions where centimetric accuracy, decimetric accuracy can be achieved for these specific markets that we've mentioned, right? The automotive market, especially with the autonomous driving, electric car, etc. So this is gaining momentum as we speak, but also on the smartphone as well. So we haven't talked much on smartphone, but there are also different companies that are specifically targeted to improve the measurements that you can get out of smartphones, especially in urban scenarios, right, where it's most critical. So what is the next steps that we plan to follow? So basically, I briefly mentioned it before, but we want to just package Spear into a model that it's based on licensing. So we want to go to these first two elements in the GNSS value chain in order to license a Spear on their chips. That's activity number one. And then finally is the provision of added value services through the permanent VRS or other services, either here in Catalonia or in another regions of the world, right, where this is needed. So yeah, that's this presentation for me. I think, Joel, you're next, right? Yeah.
Thanks, Mikel. Thank you very much once again for your nice presentation. Okay, so Hello again. I will just now present the current status of the real-time services at ICGC and scalability for the future. I would like just very briefly give an introduction of the status of the services here at ICGC, but right now my presentation will be not full of answers, but full of questions. It's just the way to let us think about the future that could come. So just to try to understand where Union is meant to be, okay? So first of all, just very briefly, where the coarse networks are today. They are amongst the most used resources when the highest accuracy is needed. Nowadays, the core stations far exceeded the reference frame computation or maintenance, which is the classical approach. So services provided based on these networks are nowadays neat, let me say. They are based on three main pillars, which is obviously the GNSS reference stations, obviously the network control center, where we have here in our case at the ICGC headquarters, and the service positioning platforms, for example, the World Wide Web or the Entripcasters or whatever. As Mikel explained it a little bit more detail, just corrections can be provided in mainly two different representations, OSR and SSR. Here at ICGC, we are based on OSR, so providing network RTK corrections or corrections directly broadcasted from stations. And RTK or near RTK can be transmitted in two different services approximations. We are just using right now the BRS user approximations. And I want to point here that the computation relies, as we have seen before, on the user side, okay? And why do we need cores? As we also previously have seen, it's just to try to solve or correct the errors that we have even in the atmosphere or in the satellite side or even on the user side. This is just to give an idea of the errors that we could have when we are positioning ourselves in the field and the different kind of services that we can use, the local positioning services like RTK or the global positioning ones on like PPP. Union is trying to combine everything together. And I just wanted to show here perhaps the most important or used services at ICGC, the ones with the symmetric accuracy, the one with virtual reference stations, or the one coming directly from each station. They are just GPS for GPS and lunar constellations. And on the centimetric accuracy side, we have also perhaps, I think, the most used service, which is the one with full constellation, which I think is being used by the 90 or 95% of the users. As we have previously said, here the data flow is just from the reference stations to the data center. Then the user is using internet to interrogate the data center just to get the data, sending its approximate position. And now we start with the questions. I just want to show here just a couple of graphics. The first one is the different users per day that we are having here at ICGC. I'm showing the information from 2014 to the very beginning of 2023, and the hours of service provided per day. In the case of the different users per day, we have been passing from 50 to more than 350. This means a 39% average increment. And the question is, what in, for example, 10 years? Are we going to be serving nearly 1,500 users? 4 times the users that we are serving today? I don't know. That's the question. And from the hours provided, we have moved from 100 to nearly 2,000 hours. This is 51% average increment. What in 2033, just in 10 years? Are we going to be serving 8,000 hours per day, which is 4 times the hours that we are serving today? I don't know. What we will be serving in 10 years, what we already know is that the serving is growing. That's a fact. I don't know where we will be in the future, but I know that in the present, the service is growing a lot. For example, just to give a brief example, which is, I think, an exit scenario, which is the precise farming. We know that precise farming nowadays is a fact. In fact, we have a lot of users coming from precise farming. They are using the services, the real-time services, the most accurate ones for fertilizer distribution, for application of herbicides, for phytosanitary treatments, for sowing and harvesting, for everything. And they most of the times need the highest accuracy, as if they were surveying in the field. Here you can just see 3 small snapshots where you can see the users. These are obviously farmers just working in their parcels, just to give you a brief example of what we are having. And if we look at the statistics, this is more or less the same. This is saying just exactly the same that we have seen for the users. We are facing a 20% average increment for the annual entry users connected. Should we expect 4,000 different users per year in 10 years? I don't know. There's a 71% average increment for the annual hours provided for the farming. They are quite an intensive users. They start working, and most of the times they are using the service continuously for 12 or 18 or even 24/7. They are quite intensive. Should we expect 10 million hours in 10 years? I really don't know if this will be the situation or not. This is just the current picture. This is just the usage that we have here in Catalonia. We know that we have guidance machines, we have farming, we have civil works for canals, pipelines. They're using bathymeters, civil works, surveying. This is the real usage that we have right now in Catalonia. Obviously, I don't know the future, but this is the current situation. And just to give the summary of what we have here, the entry services in general, we know that they have been growing a lot. The precision farming, just to give an example, it's also growing a lot. And what if right now we are at the beginning of 2017 growth that we have seen for the agriculture, but for automotive or LBS sectors? And we know about machine guidance and precision farming. We are right now in the situation of thinking about autonomous driving or smartphone positioning, as Mikel already said in his presentation. But what about, for example, drone navigation, sports monitoring, emergency serving, fleet management? What's the user, which is the user that's going to need our services in the future? We really don't know, but perhaps we are moving to a new standard. And we need to start to think about it. If you remember, I showed this information previously on my last presentation, where I showed you the need of resources for the permanent VRS system working on a Linux server. I just want to show here the real performance of a server just giving right now the services of the CatNet network. The CatNet is running on a couple of servers, Windows Server 2019 servers, 64-bit servers. They are mounting 4 CPUs each, so 8 CPUs, 12 gigabits of memory per each, so 24, and a hard disk of 320 gigabytes. This has nothing to be in comparison with this. But the servers, if you remember, this was working at the 1%, but these are working between 30 and 70%. This is 2 days. Just to let you know that the servers are working a lot just to provide the services. Obviously, you are just here seeing probably the peaks of use. So when there's more demand on the field, the server needs to process even more, just not to solve the network, just to provide the service to users. So this is increasing. As you can see, there's a big difference between this and this. This will be needed as the service that we are providing right now needs to be there just to be able to generate this. But how much this can be growing in the future, you know. And the same for the bandwidth. This is the bandwidth that we are monitoring right now when providing the service to the users. Now we know that we have more or less 10 megabits of data throughput just going through the net to provide the services. This is the traffic going out. But what if instead of having 150 users, we have, I don't know, Mikel said thousands, hundreds of thousands. I don't know what's the amount of bandwidth that we'll need. But here is where Union is meant to be. I mean, we know that we need to start thinking in some other solutions just to be able to fit these needs that could arise in the future. And as I say in my conclusions, we don't know where the future and positioning will bring us, at least I don't know. But we know that usage is growing and technology is evolving. And we don't know if Union will be the technology to be adopted, but we already know that the new technologies will come and Union is already here. So Union is a technology, as we have already said, based on new technologies or classic technologies that we are already in use. They are already checked, so we know RTK, PPP, or HAS. But we are also implementing a new concept, which is the permanent virtual reference stations. We are combining everything in a new location stack, as Mikel said. This is the software that's running on the back of Union just to be able to provide all this to the users. And this was my reflection here. So I think right now we are moving to the demonstrations. So Mikel is going to show some videos to us, and I think he's going to join with some of his colleagues at Rokubun. So.
Yeah, so before we go into the demo, I just wanted to give a couple of comments on your presentation, Joel. Let me just reuse. You had, yeah, this one. So if you remember from my last presentation, I mentioned added value services are going to explode in the next 10 years and are going to increase by a rate of 72%, which is close to that figure here, right? So, so I'm happy to see that actually this is not a forecast, but also somehow backed by actual numbers. So at some point, I probably would I would suggest you to talk to the guys at USPA who made the GNSS market report and let them know those figures, because I think that's a valuable set of data you have, because it's actual data, it's not forecast. So that's also relevant. Another question I'd like to make on top of your presentation is the fact, yes, so we overcome this scalability problem. I think we have some minutes, right? We have partially solved these scalability problems in terms of permanent virtual reference stations, because we removed the bidirectional nature. But there is also the fact that we can still saturate the server if a lot of users are asking for the service for a specific particular area, right? So one of the possible solutions to that is by edge computing, right? So segmenting the whole network into different subnetworks that are served, for instance, for base stations that are attached to telephony or cellular networks, right? This is actually something that is being investigated. So how can we segment a network and serve specific local streams of data to a massive number of users? This is probably not a communication navigation problem, it's more a communication problem, but still is there, right? So this is something that might palliate the effects you mentioned here on bandwidth, on computation power, because you are also segmenting the amount of processing load that you need to perform, right? So these are just a couple of digressions that I had. Okay, yes, as Joel was mentioned, we wanted to show you a couple of videos for that. For that, I'd like to invite Maggie here. So unfortunately, we have two presentations or two videos we want to show here. one automotive and one smartphone that is going to be presented by Maggie. Unfortunately, because of the logistics, we cannot, say, bring you into a car and then a 100-mile drive, right? So we had to refactor this demo, and we make a short video like showing how it performs in different urban or in different scenarios, urban, automotive, loss of log, etc. This is a really short video. I think it's 1 minute. And you will see basically 3 windows here. This is actually the front end of Medea, right? That you can see when you're running Medea with our processing engine. That's what you would see in your smartphone, or if you are connecting to Medea with a laptop. This is from a laptop, right? So basically Medea raised a network, and then you connect to the network that is generated by the receiver, and then you can see this, right? That's actually what you would see. What you see is what you get. All right, so we have different windows here. We have the position, we have velocity, the SNR of the different satellites that you are going to be seeing. Obviously a map, that's a given, right? For a positioning solution, you need a map always. And here, for the sake of this demonstration, we just put 2 positions. So the one you get with our engine in yellow or orange, and the one of the truth, which is basically RTK position by a, say, commercial solution, commercial and proprietary, right? The test was taken with a car with automotive antenna. Antenna, it's a mount, it's a magnetic mount, so it's not a geodetic antenna, so to speak. And both the reference receiver and our receiver were in a zero baseline test, so they were seeing exactly the same observations. Here we also put the difference, the horizontal error between the 2, so you will see that they are mostly within 1 meter or even less, centimetric, decimetric, which basically fits on the main requirement for that demo, which is we want to achieve lane level navigation, right? So I just will go through this. Let's see if nope, okay, not this button. Okay, so this is in urban scenario. Right, it's, if I'm not wrong, this is San Andreu de la Barca. Then we went through a highway. This is open sky. In principle, is good conditions. We were receiving OSR corrections for that. Right, so as you can see, we are achieving a lane level navigation, which is one of the objectives of the project. So far so good. And here is one where we lost the visibility. So whoops, we got the reference receiver, as far as I know, it's propagating the solution, so that's why you could see some points inside. And then finally, we got here some station change, right? As we were moving through the highway, obviously there were some permanent stations that were lost, so we had to attach to other ones. So that's why we wanted to make these long drives, right? So to test the different transitions between one station and the other. So this is as far as the automotive is concerned. We can repeat them later on if you want. So Maggie, you want to join us? So while Maggie's preparing this, Maggie is a GNSS engineer as well that joined Rokubun several years ago, like 2 years already, Maggie? 2 years and 3 months, yeah, quite a lot. Do you have this, maybe?
Okay.
Or
so
if not,
I'll sit down, maybe.
Yeah. You want to use this, maybe?
No, it's okay. Okay. Well, it's working.
So what Maggie is going to show is, as you say, as we said before, we implemented the solution for automotive and also for a smartphone. So Maggie has been working on the smartphone side of things, right? So she has been taking the positioning engine and then embedding it into Android. So preparing all the libraries that are needed to interface the smartphone with the libraries, also making the campaigns, the test and validation campaigns on the smartphone side. Smartphone is a more challenging environment, as you will see. It's the receiver. So a smartphone doesn't do positioning, right? A smartphone, what it has to do is safe battery life, right? So if for this it has to sacrifice GNSS, it will sacrifice GNSS. So the antenna is not great either. So it's a whole different beast that is sometimes difficult to tame, right? Yeah, that's in the desktop. You have a demo. You want the slides or the?
We can start from the slides. We have just 3 slides for you. Oh, perfect.
Yep. I think you can use this. Yeah.
Fantastic. Okay. Oh, it will not be that visible, so. Okay. So, as Mikael said before, Spear is an agnostic platform which gives us the opportunity to work on different devices, more and less professional. So, on top of the C code, with all the algorithms, we added the library in Java with basic interfaces for the developers, so that they can later on use Spear in handheld devices. And internally, we're handling all the data reception, first data management, sending and receiving from Spear. Actually, I would add one comment to previous presentation of Mikael, because he mentioned that the market is quite competitive, which is true for more professional devices, but I think in case of smartphones, the one competitor is just Google. We have a lot of applications which are responsible for creating RTCM also, I think, but RINEX data or reception of the signals, but no one really created the algorithms to receive the positioning in smartphone. And why? Because it's super difficult. The data quality is not that good. The overall data management, moreover, like GPS chipset is quite a black box, because when we buy a smartphone, we don't really have much information about GNSS in the smartphone. Sometimes the manufacturers tell us about the constellations, but not often about the frequencies. And then data management, also as Mikael said, data memory consumption, moreover, the threading, which is also a big problem, so that on top of all these layers, I think many companies decide to create the products for more professional devices because they are sure of the quality of the data rather than for the smartphone. So that, yeah, we make it more challenging for us to create the positioning engine which can be used across multiple devices, but we need also some independency of Google at some point. And especially we can focus on Galileo with the European project. Vale, so coming back to Union, we run the tests and store the logs, so that here you can see that smartphone connected properly to the Unioncaster received the data and decoded the data. And in the table you can see the messages, the RTCM messages, and the amount of the messages received from the Unioncaster. So we receive all the 4 constellations, GPS, GLONASS, Beidou, and Galileo. Later on, they are being held in and processed in Spear. Okay, and that's the real-time solution. I'm sorry. I might need help to switch it off. Oh, okay, thank you so much. Okay, so we do a lot of testing. We do a static test because we have a permanent antenna in our office. We use cycling tests, automotive tests also, but for the sake of this presentation, we decided to make a test also nearby in the Montjuic. And in the plots, we see 2 solutions. One is from Android fuse location provider, the other one from Union. And what we can see also is that fuse location provider is a mix of GNSS solution plus sensors plus smoothing plus assisted GNSS. So overall, it's much more smoothed.
But at the moment, we are masterpiecing the GNSS positioning engine. So yeah, and we can see an extreme improvement from the first day when we started using the positioning engine in smartphone till now. And just worth to mention, because during the networking session, we'd like to invite you, if someone would like to go out and test the smartphone positioning engine. We have Pixel 4 that we're using at Rokubun. We can go outside and we can do some tests if someone is up to. Also, just worth mentioning is like we check the sky plots around here, and basically we have no visibility on the north side of the sky. So in case another side is covered by building, trees, whatever, we can expect some accuracy decrease. So, and now let me show you the video. Okay, so also, thank you. Also, I can add that there's a real-time demo. So we'll see two solutions. One is provided by Fuse Location Provider, the other one from Sphere. But also Sphere, exactly, it's speeded up. I was walking, but it would be too long. So the orange circle is our Sphere, and the default blue dot is I think it's visible. And the blue dot is Fuse Location Provider from Android. We also collect data, so we can do real-time and post-processing. Yeah, so. From my experience, sometimes Sphere provides better accuracy than Google, but yeah, as I mentioned before, Google is much more smooth because that's their priority, what we've noticed. So we can also see that at the moment when we entered the park and we were surrounded by trees, there was a moment when Sphere got lost, but quite fast got the correct position again. Well, that's it. Thank you.
Okay, so thank you. I think that we have reached the end of the presentations. I think that we are also a little bit ahead of the schedule, but we can move to the questions. If you have some of them, we'll be here trying to answer them. So now it's your turn. One at a time. Yeah, sure.
Thank you very much for your presentations. I would like to know how your system is affected if any of the cores is down from the system.
The permanent virtual reference station, you mean, more or less? That's performing exactly the same way that it is performing for users. I mean, as the station, if a station falls down, so it's not able to provide the solution, the software in charge of providing the solution just starts recomputing all the permanent virtual reference stations and start providing the solution from the closest one. It's just like any other user. If a user is just working close to Lleida, but the user fall down, the server itself just changed the station from Avellanes, for example, which is the closest one, just to start providing corrections from this station. So in the permanent virtual reference stations, it works exactly the same. In fact, we did some testing just like this, just closing some stations, just checking that sometimes this can affect to 20 or 25 stations, but just in, let me say, a second or a couple of seconds, all the permanent virtual reference stations are just up again. This is why in the figure is shown the data availability. You just see 99.9 or 99.8. This is the gap that we are suffering when station is down. I mean, we were just checking what's happening on this situation, and we were just seeing that the software was capable of reprocessing this very fast, but obviously it requires some time.
Okay, thank you.
Thank you. Any other question? Xavier, please.
Yes, thank you for nice presentations. Yeah, my question is probably to both of you, and it's about portability. For a standard commercial navigation solution, would it make sense to embed Union in it? Is it possible? Is it straightforward? What's the status of that?
At least from our point of view, I think that it should be feasible, as the service is already there and the software performing the permanent virtual stations is already there. But I think that from the user point of view, Mikael for sure will give us.
So there are two things to consider here. One is the compatibility between the network and GPS receiver, but as Joel was saying, it's standard RTCM messages. So from that point of view, it's not a problem. Everything should work out of the box. Now, there is the thing of embedding the whole algorithm into the platform. This can be tricky because even though we process low level and it working on an ARM devices, there is still some work to do in that sense, especially if you want to target to automotive applications, for instance, right? You have to pass certain requirements of safety. These have to be met. But as a general rule, as the state is of now, it can be compiled and it can be embedded, and it would, in principle, work. It depends also on the architecture of the receiver itself. Right?
Are you considering to extend the zone of Union out of Catalonia?
Not from our point of view, at least, because we are really faced in providing services here in Catalonia. I don't know if in the framework of the project this would be feasible, and I don't know if Rokubun is thinking about it.
Yeah, the architecture, we know already how an architecture can be built with permanent VRSs. The natural step would go beyond probably Catalonia to the rest of the Spanish territory, where they have RTK networks, but they don't have such a system, for instance. There are other countries, like France, for instance, but they already have quite a dense GPS network receiver, so maybe it doesn't make much sense in that case. But there are other countries that they don't have so much of a dense network, and then it could be viable to go to these countries. Maybe in the form of public institutions that have already some network deployed, and then we could leverage that. Or maybe leveraging some privately owned networks, such as I was mentioned before, the Swiss network, Swipos, has already an RTK network, but it's premium. But it could be also exported to that case, yeah.
Sorry, I have a new doubt.
Sure, that's your turn.
We have been speaking about an unidirectional service. First you connect, the system needs to know where you are to provide your corrections. So I imagine you need to send your NEMEA position. How is it managed inside the system when you are moving and you change your position? So it needs to give you the information from other different permanent virtual reference stations.
This is in fact managed in the UK.
Sí. Yeah, so basically we have the source table. The source table has all the mount points in the receiver, I mean. So you have all the mount points as well as the coordinates of each mount point. So the user can select, if you tell it, okay, I want auto-basing, like for instance, for one station. So it would look at the closed mount point and then attach to this mount point. If you tell it to be, I want to be connected to 2 or 3 simultaneous mount points, it will look for the 3 closest based on the source table and connect to those 3. Does it answer your question? Or? Mm-hmm.
So it is you, the one that selects the mount points where you want to connect.
Exactly. Eventually, the receiver decides which mount point to connect to.
Okay, thank you.
Any other question? Okay. If not, as Maggie said, after now we are having some networking snacks, just where we got the coffee at the very beginning. And after that, if you want, we have the hardware here just to do some live tests. If you are interested in this, just let us know in the networking snacks, so we can just make a small group or whatever if we want to go, all of us, and we can just move out just to show you, and you can just check it by your own. Or if you have any other thing, for sure we will be there. Just come to us if you have anything that we can address. So I think that's all for the workshop and demonstration, more or less. Thanks for coming here. Thanks for joining us in the live event. We hope that it was very useful for you, and we'll be here just in case you need to reach us.
Thank you for your time as well. Yeah, thanks.
Thanks.